Lawrence Hall of Science is the science education center on the Berkeley campus of the University of California. Since 1968, the Lawrence Hall has served the public, teachers, and schools with innovative programs designed to foster greater understanding of science, mathematics, and computer technology. It has done this in three ways. As a discovery museum, the Lawrence Hall enables visitors to explore science through exhibits and laboratory activities. As a research and curriculum development center, it has gained an international reputation. The programs of the Lawrence Hall of Science have been translated into more than 18 languages for use in schools around the world. And across the nation, teachers consider the Lawrence Hall a valuable resource for training and updating their knowledge of science, mathematics, and instructional uses of computers in the classroom. The Center for Multisensory Learning at the Lawrence Hall of Science serves the science education needs of disabled students. Its programs reflect a philosophy of student inquiry and problem solving. Through a multisensory hands-on approach to learning, the center's programs make science more accessible to all students, regardless of their disabilities. Activities from two of these programs, science activities for the visually impaired and science enrichment for learners with physical handicaps, are featured in this video refresher course. Although the SAVI and SELPH programs were developed for disabled students at the elementary and junior high school levels, now these programs find numerous applications in a much broader cross-section of American education. These carefully crafted programs enable all students to work with their teachers and enjoy the satisfaction of discovering science firsthand.
Greetings from the Center for Multisensory Learning at the Lawrence Hall of Science. I'm Larry Malone, and I would like to use the convenience of video technology to provide you with a brief introduction to one of the modules in the SAVI-SELPH program, Magnetism and Electricity. This important content area is found in many elementary science programs, and we would like to look at the way SAVI-SELPH deals with this important content area. First off, the teacher's instructions or activity guides come in a package like this one right here. Inside you'll find individual activity folios, one activity for each of the activities, and they're sequenced. This is an overview folio that's also found in there, and this provides general information about the program and links the activities together. In addition, we have a package of student materials. In this box are all of the materials needed for the students to have a hands-on experience with all four of the activities. Students work in small learner groups. The materials in this package will accommodate up to 8, possibly 12 students to have a quality hands-on experience. Let's look at the organization of the program. These are the 4 activities in the Magnetism and Electricity module. The first activity is called the force, and in the force, students learn about permanent magnets, they learn about the ideas of attract and repel, and discover the force responsible for these interactions. The second activity, called Making Connections, the students make circuits and investigate the ideas of conductor and insulator. The third activity is called Current Attractions, where they put the 2 previous sets of ideas together to make electromagnets and to investigate magnetic strength. The concluding activity, Click It, is an application of all of the learning that's come before, where they make a telegraph unit and invent a code in order to become involved in telegraphic communication. What I'd like to do now is run through each of the activities very rapidly, and let's start right at the top with the force. I have to go to my box now and pull out the materials that I'll need. First off, I'll need magnets. And I'll need a set of mystery objects, which we'll use in a moment. These circular magnets are distributed, 1 to each student. The students then investigate them, discover their properties, discover how they interact with materials in their environment, and then are invited to get up out of their seats, move around their environment, and see what the magnet sticks to and what it doesn't stick to. They come back to their seats, have a short discussion of what they discovered, And then they turn their attention to the mystery objects. Now, the mystery objects are really no mystery at all, but they are objects that have properties that will be of interest to the students. They then, without using their magnets, predict 3 objects that they think will not stick to a magnet and 3 objects that they think will stick to a magnet. They then test using their magnet to see how their predictions hold up. From this experience, we generate the idea that magnets stick only to iron and steel. That is to say, the materials that they find in their environment that the magnet sticks to, only iron and steel. Next, we want the students to find out about the interaction between 2 or more magnets, to find out about attract and repel. For this, I'd like to invite you into a training session that we conducted some weeks ago, where teachers, playing the roles of students, learning to use the program in their classrooms, are enjoying and learning the SAVI-SELPH program. Based on the experience that the students have during this free-form activity of investigating how magnets interact, the students then have the opportunity to attach the language of attract and repel to describe the interactions that they've observed. For younger students, primary age students, this is probably as far as you want to go with the activity. But for more advanced students, upper elementary age students, we'll want to go further and investigate the force of attraction between 2 magnets. To do this, part 2, we'll need to get more materials out of our box. We'll need our balance, more magnets, some weights, and some spacers. The balance is set up as it always is. But now I'm going to take another magnet, this one stuck onto a little post, and insert it right into this little well here in the base of the balance. Now, when I take magnet cups and insert them in here, cup A will stick and cup B will be used for balance. Now, to reinforce, attract, and repel, we can use the magnet cups in such a fashion. One cup, when it's inside the other, repels, floats. Students find this to be quite interesting. When the 2 magnets are put base to base, the cups stick. And from this, we can invent or reinforce, depending on where the students have been, the ideas of attract and repel. But now we want to get on with breaking the force. Now, with this kind of a setup, by using these large washers, I can put them over here in cup B until I've successfully overcome the force of attraction between these 2 magnets. I'm looking for the one that just breaks the force of attraction. So in such a process, I'm quantifying the force of attraction. Once I discover that, I can use these little spacers, plastic poker chips, and place them one at a time between the 2 attracting magnets now, and find out how the insertion of a spacer between attracting magnets increases, decreases, or doesn't affect the force of attraction. Students use this chart to record the results of their discoveries. And they use these sticky dots to stick right onto this prepared chart that is a 2-coordinate graph showing the relationship between the number of washers it takes to break the force and the number of spacers used. Let's go back and rejoin our teachers in their training session to see how they learn to break the force.
We are going to together? He wants the old bombs away, doesn't he?
No,
He doesn't?
no,
We don't have to.
no. He's showing that the bombs were long enough to be able to break it. And one. Oh wait, give me one of the calculated guess before we.
No, 13. Because I took 2 out. Now it goes at 14. Janet, maybe you had a more evenly distributed. So we need this. I think 15.
Now we have 3 spaces in there, right?
3 spaces.
All right.
No, 16.
How many do you think it will take
2.
to break it? 2. It took 18.9 for 1 spacer. Let's see. Now for 3 spacers. You say 2?
I say 2.
2?
But you know, you are gay, so go on. Just like Lily myself.
I would guess.
Gay. Oh, you're such a busybody. It's just a joke.
I'm going to guess 4.
4?
Yeah.
For 3 spacers.
Yeah. So we got 1 in there. Don't bomb
No
away.
bombing.
No bombing.
No bombing. Look, also we have these different sizes.
Okay, there's 2. 2.
Shoot. Smart aleck.
3.
Oh, there it goes, down the drain.
4.
It won't hold 4, it'll hold 3. Can we put it right on the line?
Right at the intersection.
Yeah.
And then for 1 spacer was
9, right?
9. Yeah.
Put it in here. Right. Can you put it here or here? Right on the intersection.
Yeah.
With the intersection. So this should be over here, huh?
Yeah. Oh, that's it. Before we do it, I think it's going to stay a lot. It's going to be way high. It's going to be the same arc, but much more. It's going to take.
It's going to take a lot more.
Oh yeah. For each one. You mean? So what did it? You mean?
It was 14 was our
I'd say
30.
19. 19.
This is the kind of chart that you saw the teachers generating. It's a nice curved affair here that shows the continuous relationship between the strength of the force of attraction between 2 magnets and the distance that separates them. Now, following this kind of an experience, the students are prepared very often to travel paths of extension. SAVI-SELPH provides many opportunities for exploring related areas. For instance, the students may want to investigate what happens to the force of attraction when we increase the distance between the 2 magnets, not with plastic poker chips, but with steel washers. Does the force increase, decrease, or is it not affected? Students may want to investigate the force of attraction between 2 magnets when the distance between them is increased with more magnets. Again, what happens to the force? The students can design their experiments, gather their data, come in with a report for the class or for special projects. Let's leave the force now, and let's turn our attention to the second activity in the module. This is called making connections. Once again, I'll have to turn to the box and bring out new materials. First items I need are common dry cell and a little motor. Students are challenged to see if they can get the energy stored in the dry cell to operate the little motor. And through experimentation, they soon discover that by touching one clip to each end of the cell, the motor operates. We use motors for the obvious reasons. They're multisensory. You can feel them operate, you can see them operate when you've got a flag attached to the shaft, and you can hear them rotating. Following this simple discovery of the most fundamental principle in electricity, we bring out an organizer. This is a simple circuit board, and I can place my cell into the holder, and now I can use the clips to make a permanent, simple circuit. From this experience, the students are introduced to the term circuit and described as the pathway that electricity travels in order to operate an electrical device. We then introduce another gadget. This is a switch, and we make one big circuit with all 3 of the objects, and now by using our switch we can take control of the circuit. The leads are kept short, and everything is sturdy in construction so that we'll have a successful experience in the classroom. Now we want the students to discover about conductors and insulators. So we invite them to throw the handle on this little knife switch all the way back. And now, once again, calling on the items that we used in the force, the mystery objects, students are challenged to find 3 objects in this set that they think will complete the circuit, and 3 objects that they think will not complete the circuit. They then test. If it won't complete the circuit, it's identified as an insulator. If it will complete the circuit, it's identified as a conductor. So the students investigate the mystery objects to find out which are conductors and which are insulators. The last part of this activity, making connections, we need 2 more, actually 3 more pieces of equipment. I need a string, and I need 2 clip leads. Clip lead is just a wire with a clip at each end. I'm going to open my circuit now between the switch and the motor. I'm going to clip 1 clip lead onto each end of my open circuit. I'm going to take the string and I'm going to tie a knot in one end and run it through 1 hole in my circuit board and then down through the other hole in the circuit board and tie a knot here. And what I've effectively made is a necklace, an electronic necklace. And now when I close the switch on make a closed circuit out of my switch, I have 2 probes that will allow me to go around my environment and test to see how much of it is made of conductors and how much of it is made of insulators. The only rule is you never test wall sockets. There's another rule too. You never test anything on a person without first checking with them. Let's go back and rejoin the teachers now who are involved in exploring their environment to see how much of it is made of conductors and how much is made of insulators.
Okay. So what is that? Chalkboard?
Yeah, chalk tray, metal.
Tray is insulator, huh?
No, it's conductor.
Oh, it's conducting?
It's working.
Oh, it's working.
Can I have your jewelry?
No, it's going to conduct right along with me. Oh, it didn't go.
Yeah, there it did.
No go, huh? No. They're connected. You'd think they would.
How about here? Put on one on each side. Put it on the frame.
Well, wait, let's,
Does it work?
no.
No? Alright. Try the door now? That's what
Try
it
this. It works here, huh?
Yeah, that is.
Oh, it hurts! You gotta put in the same filling, too. No.
Yeah, I didn't.
No, the filling was.
No,
But 2 sides of the same, something's happening in there. There's a lot of insulation there.
Did that look like fun? Believe me, it is. But there's more. We're going to go now right into the 3rd activity in the module, current attractions. Once again, we'll need more materials. Our familiar circuit board, of course, will come into play. I've already got my cell in place. I've got my switch screwed down permanently to the circuit board using a screwdriver, and I've got a clip lead all ready to go. I'm going to need this bolt, got a nut glued in place, and I'm also going to need this piece of wire. I'm going to use these new materials to make a magnet. The solution is to wrap the wire around the bolt between the head and the nut that's glued in place. Doesn't have to be fancy, just get it on there. Now, when I clip this new device into my circuit, first, before I do that, let's see if we've made a magnet. This is important. No magnet. It won't pick up any of these tiny steel washers. But if I clip it into my circuit, and now, when I close my circuit, lo and behold, a magnet. Very exciting to youngsters. And when I open my circuit, it drops off. The magnetism disappears. I can record the results of my experiment in my sorting tray. When I lift a load of these little washers with the electromagnet, I can deposit them right here in this first circle in the sorting tray. The wire I used was 50 centimeters long. The first effort is called Trial 1. I can record by putting the washers right here. I also want to conduct a second trial. Now, I want to see if I can adjust one of the variables and change the amount of magnetism. For this, I'll need a second bolt, identical to the first, and another wire identical in every way except much longer. In fact, 150 centimeters long. Again, without any ceremony, I just want to wrap the wire into that space between the head of the bolt and the nut that's glued into place. Now when I put my new electromagnet into my circuit, I can test to see if there's any change in the strength of the magnetism. And I find that, yes, I can lift a great number of washers. And once again, I record by placing those into my sorting tray in the section called 150. As you can see, we've set up a situation where we've bracketed a 50 centimeter wire and a 150 centimeter wire. We've bracketed an intermediate value, 100 centimeters. We then challenge the students. If we had a 100 centimeter wire, how many washers do you think you could lift? Based on the results of their experiments, they should be able to predict an intermediate value. We then provide we provide a 100 centimeter wire. The students do the experiment and verify their predictions. That's the conclusion of current attractions. But we're going to move smoothly into the last activity, click it, using some of the same materials that we've used in current attractions. I'll need my screwdriver, certainly, but I won't need my little washers. I'm going to need my 150 centimeter wire electromagnet, and I'm going to need this piece of spring steel, which I'm going to attach to my circuit board. Now the screwdriver becomes all important because I'm going to assemble all these gadgets into a telegraph. Now on the top of my board is a tiny hole that will just accommodate the screw for the piece of spring steel. And at the bottom of this irregular cutout shape is a hole that will just accommodate the electromagnet. And when I screw these down using my screwdriver and get them all oriented properly and hook them into a circuit, I end up with this configuration, a circuit composed of cell, switch, electromagnet, and back to the cell. So let me hook this up. Let me take my cell and place it into my new circuit here. And now, if all has gone well, when I close my switch, it should activate the electromagnet and pull the piece of spring steel over, which it does. Each time I close the circuit with the switch, or as it's known in telegraph parlance, my key, I get a click. And we've recapitulated the history of electric communication. Now, when Morse invented this gadget, he also invented a code, still in use today, the International Morse Code. Too difficult for youngsters just learning to use circuitry like this, so we've invented a much simplified code. We call it the click code. 1 click equals one letter. 2 clicks equals another letter. 3 clicks, and so forth. And we found that up to 6 letters in your abbreviated alphabet provides you with sufficient versatility to make lots of words. We suggest the letters in the word stream, S-T-R-E-A-M, 1, 2, 3, 4, 5, 6. So by sending a sequence of clicks, the students are able to communicate back and forth using their telegraph unit. The very last thing that the students do with their telegraphs is to use these long wires, we call them the telegraph lines, and actually wire 2 telegraph units together so that now one student or pair of students can be working here where I'm sitting, and another pair of students at another board can be out in the hall, in another room, where the telegraph lines extend to, so that now they can't see each other, they can't speak to each other, they have to depend on their telegraph units to communicate. It adds a lot of color and excitement to the activity and opens the door to electronic communication through some of the contemporary ham radio networks. That brings us to a conclusion with the activities in the Magnetism and Electricity module, and I hope that you'll have an opportunity soon to get a hold of a kit, get a hold of the printed materials, and introduce your students to some of the excitement of magnetism and electricity in your classroom.
For information about additional video refresher courses in this series, contact the Center for Multisensory Learning, Lawrence Hall of Science, University of California, Berkeley, California, 94720, or call area code 415-642-8941.